Hello and welcome. So in this video lecture, we are going to talk about the allowed constructs in Shroik, and as well as we'll talk about the semantics of different Shroik constructs in the light of model theoretic semantics as well as in the first order logic semantics. And then finally we'll summarize by relating different logic families in description logic. Right. So let us first start with the allowed constructs in Shroik. Right. So allowed constructs in Shroik. Now, as we know that we have got three different boxes. One is the T box. The second one is the R box. The third one is the A box. Right. So let us see what are the things that are allowed in T box. So you can allow atomic roles. So atomic roles are allowed. The top concept and the bottom concepts, they are allowed as we had in the earlier cases. Negation of any arbitrary concept expression is allowed. So these are all coming from ALC, right? C intersection D is allowed. C union D is allowed. Nominal is allowed. Universal restriction is allowed. Full existential restriction is allowed. So this is something which is there exactly in Shroik but not in other language family, is to define a reflexive class. So we are saying that this relation S is a reflexive relation. So for example, if you define something like self-taught students, right? So in that case, teachers will be considered as a reflexive relation, right? And the set of individuals that are related to itself via this relation will be becoming the member of this class, right? So this is allowed in Shroik. And also the qualified cardinality restrictions in terms of the max cardinality restriction less than equal to RC and mean cardinality restriction greater than equal to RC. So let me replace this R with S with an intention. The intention is that, as we have mentioned earlier, that only simple roles are allowed to participate in self and the qualified cardinality restriction, right? So that's why we are using this S in place of R. So S stands for simple roles, right? But you can use any complex role in case of universal restriction as well as existential restriction, right? Now in R box, in the first place, this R box is a regular R box. So the R box should be regular, and we have already defined what we mean by a regular R box, right? And it should be of the form S1, S2, then Sn R, right? We can define a property to be reflexive. We can define a property to be irreflexive. Let us represent that with IRR. We can define two properties to be disjoint S1, S2, and all these should be simple, right? And added to that, uh, the transitivity is allowed because this includes ALC, right? Transitivity is allowed, and we can infer symmetric property to be symmetric. So this we can derive from the existing things, right? We have seen this earlier. So in A box, what we can have class inclusion, we can have property assertion, and we can have negated property assertion, but this negated property assertion is holding for only simple rules. But for simple property assertion, you can make use of any complex rule, right? So with this, let us get into the model theoretic semantics of Schroik. And to remind you, the model theoretic semantics will look forward to representing every class expression as a set, right? Now we have already defined all these things. So all these things we have already defined. So we'll be defining this, and this in the T box, and in the R box we will be defining this, and this, and in the A box will be defining only this, right? Because other things have already been taken care of. So we are talking about the model theoretic semantics of Schroik, right? So let us first define there exists S self, right? So that means let us try to visualize what we really mean by this. So you have A, and A is connected to A. It has got at least one relation which connects to itself, uh, mm, and the relation is S. So let us take the case of E dot by. So let us replace S by, say, teaches, or E dot by, right? Now you can have another outgoing edge from A, which is E dot by, and E dot by, say, B, and B and A, these are two different things, different from each other, right? But you have at least one relation which connects to itself. So in that case, A will be a member. A will be a member of there exists is taught by self interpretation, right? So let us try to now formalize this in a set theoretic notion, right? So it will be a set of all the individuals A such that A belongs to the interpretation of S. So here for this is taught by, the interpretation of is taught by has got these pairs in the ordered pairs in the set, right? AA and uh, you have AB, right? So I should say that there exists, okay, yeah, there exists at least one. Yeah, that is not really. So all these A's for which you have got the this thing to be there in S, that will be a member of this there exists S self, right? Now coming to the semantics of the max cardinality, less than equal to n S C S, right? So basically we'll be counting the number of S connections going out of the uh, subject, and all the values that we have in the object position, they should belong to C, right? So it will be the set of all A's belonging to the domain of discourse, and we'll first collect the set and the set of B's such that AB belongs to S interpretation and B belongs to interpretation of C, and the count of this, the cardinality of this set should be less than equal to n. This is the semantics of the max cardinality SC, right? And similarly, we can draw up the mean cardinality restriction, right? So it will be looking like similar. A belongs to delta such that the cardinality of the set that we collect from the counting the mm, objects connected to A, basically the set of B's, and AB belongs to S delta and B belongs to C delta greater than equal to N, right? So this is the model theoretic semantics of the elements in the T box. Now let us talk about the elements in the R box, right? So we have reflexive R. So we have reflexive R, right? So basically, how do we represent this? So in this case, R interpretation would be a superset of the set that contains all the elements that are connected by itself, right? And that X belongs to delta, right? So that then we can say that this R is a reflexive relation. Now, how do you define that R is one irreflexive relationship, right? So we have a set which is R, right? And we have another set which is the set of uh, pairs that are connected to each other, right? And it is not the case that these two are intersecting. So if you take intersection of these two sets, it will become a null set, right? So that means this set, the interpretation of this R does not contain any pair that connects to itself. That is the kind of meaning that we can ascribe to R for irreflexive R. Right? Now, how do you model disjoint RS? So basically, this will imply that the interpretation set of R and the interpretation set of S, if we take intersection of these two sets, this will become an empty set, right? Now, how do you model the R box, A box? We have already modeled the class membership and the simple property assertion. So let us try to model the negated property assertion. So the negated property assertion goes something like this, and this is defined for a simple role. So this will both way imply that interpretation of A and interpretation of B does not belong to the interpretation of S, right? So basically it is saying that these two individuals, they are not connected via the relationship S, right? Now coming to the first order logic based semantics. So if well based semantics, right? So again, let us first talk about the elements in the T box, right? So the first thing that we like to define is the self, right? So phi, there exists a self, right? So this is a class expression, that's why we'll be having only one argument here, and this will basically mean phi s x, right? So to give an example for this, so phi there exists is taught by self, right? So it will be equal to is taught by, so phi is taught by xx, and this is a kind of a very simple role. This is just a role name, and we can translate this into is dot by x, right? Uh, Now, how do you represent nominals? Again, this is a class expression, and we'll just represent this as x equal to a in first order. How do we represent something like max cardinality restriction? Less than equal to, let us first represent mean cardinality restriction. Greater than equal to n s, right? And again, this is a class expression. We'll be having one argument here. So we should ensure that there exists at least uh, n elements that are connected to x, right? So y1, y2 to yn, and for all this, they should be different from each other, right? So I not equal to j, and we say that yi not equal to yj, and so for all I equal to 1 to n, for I equal to 1 to n, you have phi s x y I and phi c y I. So basically, if we just assume that this s to be a role name, only a role name, and this class to be on C to be an atomic class, we can have an equivalent of this to be y1, y2 to yn. Then we have this the big AND. So it's just iterating over all the pairs. So that's why this is called a big AND. y1 not equal to y2, sorry, yj, and I equal to 1 to n, and this phi s will be translated to s x y I, and this c phi c will be translated to cy I, right? So assuming that this s is just a simple role name and c is a kind of atomic concept. If it is a complex concept, then we have to translate that first, then we can use this yi, right? So now coming to phi, the max cardinality is c x, right? So here we'll just pretend first that we have more than n distinct individuals that are connected to x, right? So we have more than n distinct individuals, y1, y2 to yn plus 1, and I not equal to j, for I not equal to j, yi not equal to yj, right? And the same thing, right? Phi s x y I and phi c y I, right? And I equal to 1 to n, right? And we negate this. So this is not the fact that we have got at least n plus 1 distinct individual connected to x via this relation s, right? So this is how we can translate different class expressions that are there in Stoic into their corresponding first order logic expression, right? Now let us move our attention to R boxes. So how do we translate the R box expressions in first order logic statement, right? So you can define role hierarchy. Let us try to see how we can represent role hierarchy in first order logic. First, let us talk about simple role hierarchy. So you have two roles. R1 is a subproperty of R2. Now, as we are talking about roles, we have two arguments because all the relations, they are binary relations, right? So it will be represented as for all xy, phi R1 xy will imply phi R2 xy, right? So this is the most simplest form of role hierarchy. Now let us talk about a more complex expression involving this role hierarchy. And what is this complex expression? The generic form of that is S1, S2, then Sn to R. And we are talking about roles, that's why we are having two arguments, right? Now let us try to visualize this thing, right? So what we start with, so uh, we start with x, right? And x is connected to y1 or say r1, connected to r1 via s1. Then r1 is connected to r2 via s2, and we keep on going like this. And finally we have something like rn minus 1 to y, and here they are connected via Sn, right? So if this is so, then x and y, they are connected via r, right? So this is the exact thing that we are going to represent, right? So we will use this xy to be the variables, right? And for that we need to have these things, r1 r2 to rn minus 1. So there exists at least one r1, one r2 to one rn minus 1, right? So it can have any other r or any other things, but it should have at least one r1. So there should be at least one chain like this, right? And the elements in this chain will be r1 to rn minus 1. So that is what we are making sure, right? Now we will be modeling this thing individually. We will be modeling this thing individually, and the rest of the chain will be generalizing. So that's what will be our strategy, right? So how to model this? So this is basically modeling that there is a relation between x to r1 and the property is s1, right? So we have phi s1 x r1, right? Then you have a relation from r1 to r2, r2 to r3. So basically what you have a relation from ri to ri plus 1, right? And what is the kind of connection property that we have assigned to this? We have uh, si plus 1, right? So here r1 is ri, so here s2 s is s2, so s I plus 1. So this is the property that we are having for any uh, mm, individual part in this chain, right? So that's why we will be modeling this again with a big and the big AND will have index running from 1 to n minus 2, and the relationship that we'll be having here is s si plus 1. So this is the relation that we are using, right? And the arguments for this relation would be Ri and Ri plus 1, right? So we take care of the chain here with this generalized form, right? So what would be the last part in this chain? The last part in this chain would be Rn minus 1 to Rn minus 1, and the property would be Sn minus 1. Let us check whether that is happening. So the last index is n minus 2, right? Sorry, it will be Rn minus 2. So the last value of I is n minus 2, right? So we have this n minus 2, and Ri plus 1 is Rn minus 1. So we have got the last part in this chain. And what is the property? Property is S n minus 2 plus 1. So n minus 2 plus 1, and this is basically S. Uh, uh, it is n minus 1. So is the last property that we have, which is basically we'll be replacing. So it is I plus 1. So we'll be replacing I with n minus 2 and plus 1, and it will become S n minus 1. So basically this is becoming the property level, right? So this part is really okay with the kind of modeling that we have here, right? Now we are remaining with the last part, which is basically this one, right? Now how do we model this? So basically we have the property Sn, right? So phi Sn, and this will be having our argument to be Rn minus 1 and y, right? Now if this is so, then this will imply, so the whole thing will imply that we have a relation between x and y, and the relation label will be R, right? So this is how we can represent the generic role hierarchy using first order logic, right? Now how do you model reflexive relation? So phi reflexive R x, right? So for all x we should have x, right? How do you model irreflexive relationship? We can just model it by saying that there exists at least does not exist any relation which any element which connects to itself, right? So it is not the case that there exists one element which is connected to itself via relation R, right? And finally disjoint. So phi disjoint, say R1 R2 x5, right? So we say not of, it is not the case that there exists xy, and xy is both xy is related via R, and x R1 and xy is related via R2. So this is not the case. So that's how we can represent that disjoint relationship between two properties, right? Now with all this description, more or less we are done with the description of all the logic families. Now let us try to see what is the kind of relationship that we have between these families that we have discussed, right? So the basic family that we can think of is the attributive language, right? Now if we add complex complement, basically complement over the complex class expression, so complex complement, we get else, right? Now if you add transitivity on this, then we get S, simple, right? If we add role hierarchy, then we get sh. So basically here we are using, right? Now here if we just say I, that is role inverse, then we get shi. Now with shi, if we add qualified cardinality restriction, then which is basically q, we get chic, right? Now if we add role functionality plus data type, we are adding f plus d symbol, so we'll be getting shift d. Now on top of shi, if we use nominal, then use the number restriction plus data type. So basically you are adding nominal, number restriction plus d. So what we get? We get showing, shoin, right? And with this s, if we add generalized role inclusion axioms, then qualified cardinality restriction q. So this RIA stands for R, qualified cardinality restriction stands for Q, inverse functional role R, and nominal. If we add all these things and also the data type D, we get SROIC. So we get SR OIQ D, right? Now this, all these families you can see, we could have got various other combinations, but we are really interested in just these combinations, nothing else, because these are aligned, these are all aligned with different owl families. So the chic is aligned to oil, which is basically the precursor to owl, which is the language of oil, ontology inference language, right? So chic is aligned to oil. So you can model the oil ontology language with chic, right? So Ceph can be used to model owl1 light, right? Showing D can be used to model owl1 DL, and Shroik 2, Shroik DL, Shroik D can be used to model owl2. So this is the kind of relationships that we can have between different language families of description logic. So these are the DL families and these are the owl species. And you can see that we have kind of one-to-one correspondence between different families with different owl species, right? And that will help us to model different owl species into their formal semantics using the description logic. So with this we end the portion for complete the portion for the the description logic families, and in the next video lecture we start talking about reasoning with the description logic, which is really the thing that we are working for, basically to come up with answers to our questions from the owl knowledge base and specifically to say the description logic knowledge base. Thank you very much.